All right, you know what time it is. It's time for review. Our first question, number 1. This problem, I'm first going to look at a couple things. One, it asks if the limit as x approaches 2 exists or not. And so let's take a look. Here we are at 2. We're coming in from the left, coming in from the right, and certainly it does exist. So this is definitely a valid statement. The next thing we want to check is does the value at that moment equal the limit at that moment? And I think you and I are going to say no to that because here we are, the limit comes to 1, but when I put in f of 2, I actually get a 2 answer. So I think I'm going to say no to this. This does not happen. Now, the last item is us testing 2 different locations for limits. And let's do those 2 locations. The limit at 1 from the positive side. So 1 here at the positive side would be a 1 value. And coming from, limit at 4 from the negative side. So 4 is over here from the low side. Now, this is a problem here. Actually, the limit from this side does exist, so we are okay. It's not the general limit, but from the left side, so it is also 1. So this being true and this being true means we want to circle 2 and 3, and our answer is all right, let's read carefully what we're asking for. The graph of the function f of x is shown below. For what values of a is the limit of that function equal to 0? So we want to look at a couple of moments in time. We'll look at this one. Let's look at this one. Let's look at this one. So first of all, I really like this answer in terms of a limit, a general limit at 4. I like that because we're coming in from the low side and the high side, so I'm all about this spot. Next, let's take a look at this moment in time down here at 1. I also see me coming in from the left and from the right, so the general limit would exist. The final one here, I am coming to 0, but you can see there's a jump discontinuity here, and so I do not like that. So my answers are going to be 1 and 4, and that is where I see the general limit as x approaches a, where the limit equals 0. Reading this question is very important closely. So it says, if the limit of f of x as x approaches b exists. So we have to have the limit. But it also says, but it cannot be continuous at that location. So let's move our way through here. So they say -1. Well, if I look at -1, the general limit doesn't exist here. So I'm not any good with that one. Let's go to the next one. At 0. Now, at 0, I have a limit. I come in from the low and the high side. I do have a limit, but I am continuous there. I am there. So actually, that doesn't meet both of our requirements. Let's try at 1. At 1, well, I'm not continuous, yes, but I don't have the general limit because I'm at one. The left side's coming in from the negative side, low side. I'm getting 2, and from the high side, I'm getting 1. So that doesn't have one that exists. So I'm not interested in that answer either. The next one is at 2. Now, I think I like it 2 because I see the limit. I'm coming in from the low and the high side, so the limit exists. But I'm not continuous because I have a hole there and I have this value. So I do like a 2. I don't like 3, and I think you know why. If you just take a look at it, there's no general limit that exists there. So our answer is D. All right, we're looking for a false statement. So let's go through each of them anyways, just for practice. We're looking for the function, the limit of that f of x existing at -4. When I go to -4, here I am at -4. I look at the limit. I am approaching 2 from the low and 2 from the high, so it exists. That is a true statement. Next, we are going to evaluate the limit at -1. Let's take a look at -1. Sure enough, we're coming in from the left and from the right. Our limit would be at 4. To me, all is good there as well. All right, time to check the next one. The limit at 2. Here we go. Let's go to 2. 1, 2. Aha! The general limit does not exist. We're coming in from the left and we get 2. We're coming in from the right side and we get 1. I do not believe in a general limit in that spot. So that one so far is false and probably will be our answer. But let's keep going. The limit exists at x equals 3. Let's go to 1, 2, 3. Yes, from the left we come to -1, and from the right we do. That is a true statement. And finally, they say the function f of x is continuous at 3. Oh, fun. Let's review continuous at 3. So it means it has a general limit of -1, and the value is -1. There we go, folks. We have our answer, the false statement.
Five apples, 5 trees, 5 tiny little buzzing bees, 5 tables, 5 chairs, 5 monkeys jumping over there.
In a problem like this, you have to start right away thinking about factoring, because we're looking for horizontal and vertical asymptotes. So in the numerator, I realize that I've got a lead coefficient of 7. So I'm looking for 2 numbers that multiply to 28, but add to -3. And when I looked at the guys, I thought 4 and 7 might work, but really it doesn't work in terms of being positive and negative. So in that manner, I realized that I have to now just worry only about the denominator and factor that out. So I get 7x squared minus 3x plus 4 all over x minus 5, x plus 5. Now I can start to look at the domain, the items in x that cannot be used in the denominator, and I realize that I can't use x equals 5, and I can't use x equals -5. Those are my 2 domain restrictions, which are vertical asymptotes. So the next thing we look at is the horizontal asymptote. We look at the lead dominant terms. In this case, they're both x squared. And so we learned that as the limit goes on out to infinity on that the x squared in the numerator and the x squared in the denominator, those indeed just go out to the coefficient of 7. So we get y equals 7 as the horizontal, x equals 5, and x equals -5 as the vertical asymptote. All right, here we are at number 6. So the first thing I want to do is factor the denominator. I wanted to take a 2 out of everything, so I started there and I ran into that 3 and ran into trouble. So this is a lead coefficient of 2. You remember how to do this. 2 numbers that multiply to -40 but add to -3. I do it by grouping, and there, sure enough, I've now factored it. So here's my factored form. This allows me to make some decisions. First of all, I get one of my vertical asymptotes at 4, and my other one at -5 halves, or -2.5. There is no whole or anything here because there isn't a simplifying of the numerator and the denominator. And so these are vertical asymptotes. Now we go back to the question of a horizontal one. We go to the lead dominant guy. Here is the dominant term is in the denominator, and so we learned that as the denominator gets exceedingly large, we head towards 0.
The number of the day. Really pops and kicks. The number of the day is 6.
We're going to look at two questions, number 7 and 8. These questions are just basically, do you understand what we're talking about in terms of a limit? So this says, as we approach 6, so we have our number 6. As we approach 6, a general limit from the left and the right, we are heading off into infinity. So this, of course, is a vertical asymptote, and it happens at the value as x equals 6. So the idea is, as I'm getting closer to 6, I'm heading off into positive infinity. And this is a general limit, so on the left and on the right. The other guy has a similar situation. It says, as we do the limit as x approaches infinity, we're heading out to -3. Now, this, of course, becomes a horizontal asymptote. And what it's saying is, as we are heading out into infinity, way out to the far right reaches, our graph is going to approach that -3 value. So this is a horizontal situation, and its asymptote would be y equals -3. So notice the key notation there. Horizontal ones head out to negative or positive infinity. That's a big clue. All right. On this one, we're looking at a vertical line, x equals 1, that is actually an asymptote. So this is what I've done, is I've drawn it in so I can see it. And what they're asking us for is, when would this be false? Oh, let's listen to that. Oh, okay, back to this. Now, here's the way I would approach this. If we're looking for things that are going to be false, they're going to be around what they just told us is a truth. So I'm going to look for the answer in these 3 spots, at least initially, because these are the 3 ones that tell me about the limit as it approaches 1. So I'm going to test these 3 moments, and I bet you we'll find our error. If it is a vertical asymptote, we know something about the way they work. As you get closer to 1, you're going to head off into negative infinity. That makes sense, yes. That could be something that happens. That's valid. How about this one over here? It says, as you head to 1, you also are heading off into positive infinity. Yes, that actually makes sense for a vertical asymptote. How about this one here? This is our troubled soul. This says, as we get closer to 1, we equal 0. This isn't how a vertical asymptote works. A vertical asymptote divides the graph, and we either head to negative infinity or positive infinity. So our answer is A. All right, here we are. You know what number we're at. So as we take a look at this one, it says to us that we have a horizontal line that is an asymptote at 5, and for the values as x greater than 0. So let's draw that and then see which one is true. Ooh, these are good. These will trick somebody. All right, the first one, that there could be a value, if you put in 0, you'd get 5. Now, if anything you've learned is that an asymptote doesn't mean you can never touch that line. And so actually, that's okay. It could happen, even if the asymptote is for the values greater than or equal to 0. The next one states, f of x equals 5 could never happen for anywhere on this side of the line. And that is also not necessarily true. It could be true, But that isn't exactly what it means to be an asymptote. Asymptotes happen out at infinity. The graph in the inside could do some things first, okay? So don't get hung up on that idea. This other one, this third one, f of x is undefined. I don't like that either. That isn't necessarily true. It could be. Ultimately, well, let's keep going. The limit of f of x approaches 5. Now, this is a vertical asymptote. They're just being silly. And so here is the ultimate in truth. Ding, 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 ding. That, and this is what it really means to be an asymptote, is that as we head out to infinity, we are going to get closer and closer and closer to 5. There is the answer. This question is about our understanding of jump discontinuity. Oh, wait, that reminds me. Oh, yeah, that's a good song. Now, let's take a look at A. At A, it's obvious, isn't it? There's a limit going on there. There's no discontinuity at all, actually. Next spot, let's check at B. B has a nice limit, but we are not in that space. That's called removable discontinuity. So that's not our location. I think I just found our location at C. We have a jump discontinuity there. And if we wanted to check at D, we are continuous at D. So bam, there's our answer. You might as well jump. All right, we're talking about continuous, and where do we look for continuous is right down in here. Now, a couple things are happening here. I noticed right away. X minus 5 is both in the numerator and in the denominator. So if we did the limit as x approaches 5, we would get 0 divided by 0. That's an indeterminate form. And from that, I learned that there is a hole going on at x equals 5. There's one moment of discontinuity. The next, you will see over there, my little friend, x plus 1. That also creates a problem. If I place in a value of -1 into that spot, I divide by 0 and I have a problem. This is known as a vertical asymptote. So I know there's a vertical asymptote at x equals -1. So my answer is I have a hole at 5 and I have a vertical asymptote at -1. And guess what? We do not care about the numerator.
I think I might be a little bit. This is me, 10 and 3, expecting to run out of luck.
This question is all about continuous. The definition of continuous is that the function at A is equal to the limit as x approaches A of the function. The whole idea of that is that means you have a limit, a general limit at a moment, but the point is also there, and therefore it is continuous. So let's look at what they've given us. They have given us that our function at 2 is 0. So let's plot that out. So that looks like this right here. We're here. Now let's go over and evaluate our limit. First thing you'll notice is what I noticed, is that when I factored this, these values come out. Now, you could have just done direct substitution, but you would have got 0 and 0. So 0 divided by 0 is an indeterminate form. So therefore, the factoring did help. It takes the whole out, so we can evaluate our limit at 2 of x plus 2. And when we put in 2, we get 4. So what this means is our limit is up here at 4, and our graph, our value is down here. This is called a removable discontinuity. So I like this answer, that f has a removable discontinuity at 2.
10, 11, 12, 13, 14.
I'm sure when you saw this, immediately you felt like you should do factoring. You could plug in the 4, but I think you realize after you factor that if you put in a 4, you'll get 0 over 0, and that's an indeterminate form. This is the perfect situation for factoring. This simplifies, giving us this nice limit that is easy to evaluate. And so our limit as x approaches 4 is just simply 2. It's that easy.